Now in this video we are going to solve problems based on the Gibbs free energy and also be able to predict the spontaneity of a reaction when given the entropy change and the change in the enthalpy, that is delta H and delta S. Now let us consider the reaction, that is the decomposition of carbon tetrachloride gas. So this is the reaction that we are talking about. This reaction gives us delta H of plus 95.7 kilojoules and delta S of plus 142.2 joules per Kelvin. We are required to calculate the delta G at 25 degrees Celsius and also find out if this reaction is spontaneous. And if the reaction is not spontaneous at that 25 degrees Celsius, we also want to determine the temperature at which this reaction will become spontaneous. How do we solve that problem? So the first thing is to write an equation. Delta G is given by delta H minus T delta S. Now delta H, you want to change this one to joules, so it will be plus 95700 joule, because you want to use joules, you don't want to use kilojoules. The temperature here is given as 25 degrees Celsius. So 25 degrees Celsius is equal to 298 Kelvin. You want to use Kelvin all the time. So in this case, we can say that our delta H is plus 95700 joule. Then we have delta S, which is plus 142.2 joules per Kelvin. And we have temperature, which is 298 K. So when given these three parameters to determine the delta G, you just plug them in here. So this is equal to 95700 joules minus 298 Kelvin times 142.2 joules per Kelvin. This one is going to cancel with that one, and then you just play around with the numbers. And the answer is 53324 joules, which is equal to three significant figures, is equal to 53.3 kilojoules. So that is your delta G. But as you can see, this delta G is positive. So the question A, it says determine whether the reaction is spontaneous. Then you will say that since delta G is greater than 0, the reaction is not spontaneous. Is not spontaneous. Why? Spontaneous reactions have delta G less than 0. So a spontaneous reaction is going to release free energy. Therefore, it has delta G is less than 0. This reaction is not spontaneous. And that leads us to go to answer question B. If the reaction is not spontaneous at that temperature, determine at what temperature the reaction is going to become spontaneous. Now, to solve that problem, I'll just say at what temperature, at what temperature is the reaction going to become spontaneous. So if I can go back to my reaction and get the numbers from the reaction. So first of all, I am going to say delta G is equal to delta H minus T delta S. Now, the temperature at which the reaction will start becoming spontaneous is when the delta G is 0. So, I'll just write it in here. The reaction will start becoming spontaneous when delta G will be equal to 0. So if you want to determine the temperature at which this reaction is spontaneous, you need to make delta G equal to 0. So what do I mean? I mean you want to say here 0 is equal to delta H minus T delta S, which means delta H is equal to T delta S, and that means T is equal to delta H minus or divided by delta S. Now let me get the numbers again. So in terms of our numbers, we see that delta H is 95700 0 J, while delta S is 142.2 J per Kelvin. Now when you divide those, you get 95700 divided by 142.2. So you have the temperature, because this one cancels with this. You have the temperature of 673 Kelvin. So your answer will be at temperatures greater than 673 Kelvin. So you can even change it to so 673 Kelvin is the same as 400 degrees Celsius. At a temperature greater than 400 degrees Celsius, the reaction will become spontaneous. Will become spontaneous. But at exactly 673 Kelvin, the reaction will become equilibrium. So I'll say, but at exactly 673 K, the reaction will become equilibrium. So at that point, the reaction will become equilibrium, because we know that when delta G is equal to 0, the reaction is at equilibrium. That's why when you put 0 here, you are putting the reaction at equilibrium. The temperature you obtain here is equilibrium temperature. But now when you just move the temperature greater than this, the reaction becomes spontaneous. So that's how we determine the temperature at which a reaction is going to be spontaneous, by making delta G become 0. So let's go on and look at another problem. Now in this case, you are given what we call standard entropies. The standard entropies are calculated at I'll just say 25 degrees Celsius, and standard entropies have units. Standard entropies have units of joules per mole per Kelvin. The issue is standard entropies are the entropies of 1 mole of a substance. That's what standard entropy is about. So standard entropies are entropies of 1 mole of a substance. So I'll just say standard entropies are entropies of 1 mole of a substance. Normally these ones are calculated at 25 degrees Celsius. Now, there are tables that gives you the standard entropies. So if you are doing an exam, normally you are given those tables. I'm going to get rid of this. I hope you have written it down so that I can write some more here. So normally if you are solving a problem like this one, you'll be given a problem. Calculate the delta S, the change in the standard entropy for the balanced chemical equation. So you are given a chemical equation here, and you are given the standard entropies here to solve the change in the standard entropy of the reaction. To do that, you say that sum of entropies of products minus sum of entropies of reactants. This will give you delta S, not reaction. That will give you the standard entropy of the reaction. Now, how do we deal with that in this case? These are our products. So I'll put them in parentheses. 4 times I'll just say S of NO plus 6 times S of water. These are our products. So these are products here. These are reactants. Minus, in parentheses again, 4 times the entropy of NH3 plus 5 times the entropy of oxygen. Now if you put in numbers, this will be 4 times the entropy of NO here is 210.8 plus 6 times the entropy of water here is 188.8 minus 4 times the entropy of ammonia here, 4 times 192.8 plus the entropy of oxygen, 5 times the entropy of oxygen, 5 times 205.2. So when I do that, I will just make a calculation here. 4 times 210.8 plus 6 times 188.8 parentheses minus parentheses 4 times 192.8 plus 5 times 205.2 parentheses. So after my calculation, I find that the change in entropy is 178.8 joules per mole per Kelvin. So this one is delta S, not reaction. That's how we determine the change in entropy of reaction when you are given standard entropies. So first, you say sum of the entropies of products minus sum of the entropies of reactants is equal to change in entropy of reaction. And then you just plug in the numbers like I have done here. Make sure to not forget the coefficients. These coefficients are very important. Like this 4 here is the 4 here. This 6 here is the 6 I am using here. Let's look at another problem. So this problem is like an extended one. Calculate the standard change in free energy for a reaction using this delta G, using delta H, and then T delta S. So this one is a long problem, because first you need to determine the change in enthalpies, then you need to determine the change in entropies, and then afterwards you need to plug them in here. So this is our reaction. This is the reaction. So first, how do you get the enthalpy? You get the enthalpy by saying enthalpy of products minus enthalpy of reactants. So enthalpy of products minus enthalpy of reactants. That will give you delta H, not reaction. That's what you're going to get. Now, once you do that, you can go on and look at this reaction. So here you have the enthalpy of SO3, that is our product, minus the enthalpy, I'll just say H, of SO2 plus half H of oxygen. And then you just plug in the numbers here. Enthalpy of SO3 here is given as minus 395.7, that is kilojoules. And then this one minus parentheses. The enthalpy of SO2 is minus 296.8, and the enthalpy of oxygen is equal to 0. So this one gives us minus 395.7 minus parentheses minus 296.8 parentheses. So minus 395.7 minus 296.8. So the answer for this one is minus 98.9 kilojoules. So this one is equal to delta H naught reaction. So based on that, we have found this. So we'll say that this one is equal to minus 98.9 kilojoules for now. Once we do that, we'll go again to determine the entropy, the change in entropy. So I'm going to get rid of this part. So this is a two-step process. First, you determine the change in enthalpy, then you determine the change in entropy. So I'll go on and say the entropy part. Entropy of products minus entropy of reactants. So in this case, I will say the S of SO3, which is our product, minus parentheses the S of SO2 plus half the S of O2. So the S of SO3 based on this is 256.8. Now this one is given in joules per mole per Kelvin. This minus the S of SO2 here is 248.2 plus the S of oxygen is 205.2. In that case, the answer is minus 196.6. So this is J, K, and more. So we can say that based on this equation, we know this one. This one is minus 196.6 J, K, more. So we have delta H, we have delta S. Now the temperature here is given as 25 degrees Celsius, which is 298. The enthalpy here, you need to change it to give it as joules. So you don't want to use kilojoules in your calculation. Once you get here, then you can say delta G is equal to delta H minus T delta S. Now we know our delta H is minus 98900 Joule. Then the T is 298 Kelvin. The delta S is minus 196.6 joules, Kelvin, and more. So this one is kilojoule per mole. This one should also be joules per mole. Now once you add the two, you get minus 40313.2 joules per mole, which is equal to minus 40.3 kilojoules. So for this reaction, the delta G is given as negative 40.3 kilojoules per mole. Let me just clean up here. So here per mole. But first, as I said, you need to divide the problem in two parts. You solve the enthalpy part, and then you solve the entropy part, and then you add them to give you the delta G. Let's go on. And look at another problem. So really, this problem is like the entropy one, but now you are calculating the free energy. So for a problem like this one, you say the same thing. Free energy of the products minus free energy of reactants. So in this case, you look at this reaction equation and you look at things that you are supposed to change. So the first thing you look at this equation and say, all right, what are the coefficients here that I'm going to use? Based on the coefficients, you are going to have as your products the G of carbon dioxide, that is in parentheses, plus 2G of water plus 4G of ozone minus G of methane plus 8G of oxygen. This one is going to give you the delta G naught reaction. That is the standard free energy of the reaction. Now you just plug in the numbers. So in terms of numbers, this one, we go here for carbon dioxide minus 394.4 in parentheses plus the one for water, which is minus 228.6 plus the one for ozone is here, which is plus 163.2 minus parentheses G of methane, which is minus 50.5 plus the G of oxygen, which is 0. So when you do the math, you get negative 409.3 kilojoules per mole. So we can say that delta G naught reaction is equal to negative 409.3 kilojoule per mole. So you just say the free energy of products minus the free energy of reactants. That's how you determine the standard free energy of formation when you are given a chemical reaction. So the last video will be really short. So check that one.